Hi, everybody. I want to get started now because there's a fair amount to cover in this lecture, and it will be on the exam. But I want to, I've done this lecture, this will be the 5th time. And the previous 4 times, a good fraction of the class just doesn't get it. And it's because it's got some mathematical formulae and mathematical assertions in it that are, to understand them fully, or to the level that is not like anything else I'm teaching you in the course. Now, the reason I've stuck it in here is that it is, in my view, bizarrely, the way in which internally the US government evaluates actions to mitigate climate change and lots of other environmental stuff. But to be fair to you, I want those of you who are non-quantitative to know that the exam is structured in such a way that you can choose not to avoid this question. There's enough choice that you can ignore this lecture, okay? If it looks tough to you, all right? So that's the compromise I've reached. I feel like you need to know this and have been exposed to it. If you're an economist, it'll all seem like old hat. If you're a quantitative person in general from the sciences or engineering, or from modeling and some of the social sciences, it'll feel relatively straightforward. But if you're a person who hasn't seen math in a long time and hated it, then it might be, other than the words, inaccessible in a way that string theory is inaccessible to me, because I don't know the underlying mathematics. So that's the story. All right, any questions about that before I get started? So I'm going to kind of gallop along through this. What I've done in the past is that some of the people are confused, and then I go back and I spend multiple lectures on it, and it just doesn't warrant that. My own view is that this methodology should be replaced within the US government by a different methodology that's focused on attaining an end goal, all right? Not the most cost-effective way to reduce a ton of emissions, but the most effective way to get to 0 emissions after a period of time, right? Which would be a very different methodology than this, okay? So the first thing I want to point out is something that everybody knows, and so I'm not going to dwell on it. And if you want to dwell on it, I'd urge you to look at this shockwaves report. You can get it online. And all it does is it documents the myriad of ways in which the poor will suffer because of climate change. All right, this is not a surprise to anyone. The IPCC AR6 will be divided into 3 sections. There's one on the physical sciences, there's one on mitigation, and there's one on social impacts. The one on social impacts, which is called Working Group 3, will eventually come and do a better job than this, but I didn't hear yet. This is just an example. If there's a weather-related disaster, what this shows is that poor people lose a larger fraction of their annual income. Well, duh, okay? It's right. So they have a small annual income to begin with, and if you lose everything, you're spending almost all your money on staples, and so you don't have a fraction to spend on it. This one shows that the poor spend a higher proportion of their income on food. We'll look at this later when we look at the causes of some of the violence in the Middle East, including the Syrian civil war, where the Arab Spring revolts happened, sort of perfectly aligned with the fraction of income that the average person spent on food staples. And it looks like in most places, those were the results of a food price shock. So the poor are disproportionately impacted. And this brings me to the way in which you figure out whether or not some action is cost effective or not. Should we do this? Will the outcome in terms of the good or the desirable quantities that we want to achieve, are they worth the cost? And in such a way that at least one tries to account for the differential impacts on the rich and the poor, right? On the vulnerable and the not vulnerable. And even, at least in principle, given different values that people may bring to the problem. Okay, so we'll talk a lot about this. This all falls back to a guy named Jeremy Bentham, who came up with the idea of utilitarianism as it's been taken over, discounted utilitarianism as it's been taken over by economics. So in this case, W is the current social welfare that is defined as the well-being, which is a function of future, that is years capital T into the future, consumption, C, we'll define all these again, which is the amount sort of economic consumption. You can think of it as the amount of money you have to spend. So for an economist, well-being for an individual U flows from money. And what you worry about is money that you're going to have at different years in the future from some action today. All right. That's what you're worried about. And it's because this kind of comes from businesses that have to make decisions, right? You say to yourself, well, you know, should I upgrade my capital equipment in the factory? Well, it's going to cost a bunch of money. And if I invest that money now, means profits are lower this year because I've invested it in the capital, but I'm going to make more money next year and more money the next year and more money the next year and so on. And is that a good trade-off? And there's a way to figure out that's rational. It's money to money and that sort of thing. But this has been grafted onto social welfare. And in my view, it's kind of a shotgun marriage, I got to say. All right. All right. If shotgun marriage is still something is shotgun marriage a bad thing to say now? Raise your hand if it is. You know what a shotgun marriage is even? Okay, it's a forced wedding because the couple became pregnant when abortion was illegal. And so the weddings were done by the parents at the point of a shotgun, right? That's what it's from. Okay, so is that a bad thing to say? So far, I've got no objections. I always wanted to ask that because I said that a couple of times and I don't know what's not okay anymore. It's probably not okay just because people don't know what it means. All right. Okay, sum over all future time T, this is. And so we're talking about into the future. Should I invest in my factory now? How much money am I going to get later? And is that worth it? Okay, so the first thing we have to understand is consumption in year T. And think of that as this is the money I'm going to have to spend on stuff I want in year T. All right. And utility, which is how happy I am, is a function of my consumption, the simple function of my consumption at any time. My current happiness just depends on how rich I am at some level. But to generalize it, utility's got a value, not just income, but all nexus impacts, including the value of species extinction, the loss of traditional livelihood by the Inuit, the sense of failed stewardship by an evangelical Christian. And what economists who grapple with this and the ethicists who do ask is, how much would I pay to avoid an adverse outcome that is making me unhappy, right? That's the sort of thought model that one is using. And so the valuation scheme that results obviously requires aesthetic and ethical decisions. It's not just how much money should I spend upgrading my factory anymore. It's how much do I care about stuff? What value should you put on the preservation of beauty of your favorite natural area, you being comparatively wealthy, as opposed to, say, preserving the sacred lands of some poor person in Tonga, okay? And so you're wrestling with the full suite of ethical issues almost that confront humanity, or at least a large fraction of the palette here. And so there's a gigantic amount of water. It's like dog paddling over the Mariana Trench. There's just stuff everywhere underneath that you're kind of sweeping over and saying, well, there's some function, U of C, right? Utility of consumption. But let's suppose you can do it. So we figure out some way to do it. And so having decided how to value every environmental investment and every alternative use of the same money in every subsequent year and for every single person, we then need to translate those measures into a utility function, U C of T. And discounted utilitarianism that is focused on equity assumes typically that there is a concave down function like this, in which making somebody a little richer when they're poor brings them a lot more utility than making somebody a little richer when they're rich. And this, of course, makes sense, right? You knock off a little bit of the tiny fraction of the income that a poor person has left over after they bought food and they don't have enough to pay for their food anymore. Whereas a rich person just saves at a lower rate or something like that, right? So a function like this gives priority to those worse off in consumption, okay? And so the assumption of the concave downness of something like this, how quickly it levels off, is an ethical consideration, all right? Is one that we sort of, that is just loaded with ethics. And it's one of the only places in which ethics actually fits into this business in a formal sense. Okay, now let's ask, here's 3 functions that relate utility or well-being to consumption. And what we're going to do is we're going to divide $100 between 2 people. And we want to come up with the value that maximizes their total utility, okay? Now, whether or not we should maximize their total utility, that's a separate sort of question, okay? Is it really the case that we ought to be maximizing separate utility? Is there a way to separate this so that that's the right thing to do? But that is what is done. You maximize utility. So let's suppose we're going to give $100. And if it's red, the red curve, concave down, we could give all to one person and 0 to the other person. So we give $100 to this person, giving us 10 units of utility and $0 to this person. And the total well-being is thus 10 plus 0, right? Or we could give both people $50, all right? Each person gets $50. And then the total well-being is 8.5 plus 8.5, or 17, you see? So it's bigger. The concave down shape means that if we give each person the same amount, everyone on average is better off than if we give it to 2 people separately, right? The total well-being of the population. And of course, we're not accounting for the fact that it may seem morally wrong to only give somebody 0, okay? But nonetheless, this is what's done. And if you want to maximize the utility, if the function is concave down, it's gonna move you towards an equitable distribution, all right? For 2 equal people. Now, in contrast, if it's a straight line, if you give all to one person, you get a total well-being of 10. And if you give half to each, you give each one 50 and you get a total utility of 10 again. And so it doesn't matter. You don't care about inequality anymore. So if money really does equal love, then you don't care, right? You don't care how you dole it out. If you want to just maximize the total amount of love in the world, it's just the same as how much you've invested. And finally, let's suppose that there's a utility function like this. And this is I think of this as the like super greedy person. The super greedy person, if they have $50, just thinks that's not enough. That's not enough. I want more, I want more, I want more. And I want it all. The more I get, the happier I am. It's the ravenous personality. Now, there may be reasons for this, all right? There may be regions of a utility function that might be, say, S-shaped, where if you have less than you need to feed your family, you're really pissed off and the same pissed off until you can feed your family, right? And then all of a sudden you're happier. So it's not just a greedy person. But the interesting thing about this one is that you give it all to one person, total well-being's 10, and you give half to each, and the total well-being is less than 1, you see? So what you should do is give it all to one person in that case, if you want to maximize the total utility. And of course, all that just says, in the case of the greedy person, it's because it's the greedy person's way more happy than they have any right to be. But if it's the beginning of an S-shaped function for someone who can't feed their family, giving 2 families half the amount they need to feed their family leaves both of them in distress. Whereas giving the money, saving one, I mean, it's the concept of triage in medicine, isn't it? Right? If you have a finite set of resources and you can't save 2 people, you should save 1, right? The idea. All right, so the choice of a functional form for the utility function is thus an extraordinarily ethics-rich set of decisions. Now, but in addition to that, there's an assumption made in this business that it's not just about utility, it's about when the utility happens. And this flows from the economics of upgrading your factory, that sort of thing. And why is that important? It's important because the amount of money you were going to spend on your factory, for instance, could have been used to make your shareholders richer, but it could also have been invested by you so that you're going to have it growing and have more money next year and more money next year if you don't spend it on upgrading the factory. And so the decision about whether or not to spend on capital equipment, which is going to allow you to earn more money next year and more money next year, has to be traded off against the decision to invest it and earn more money next year and more money next year. So that's the way, that investments are made around the world, right? And so let's suppose, so how does interest work? This is critical to figure this stuff out. So what does it mean to have a 5% per annum interest rate? And I'm going to mean it literally, not the continuous time e-folding interest for those of you who know what I just said, but it doesn't matter, okay? What is a 5% interest rate? It means in 1 year, you're going to take the dollars you have now, and what's it going to be worth? 5% interest rate. Well, you multiply by 1.05 to the first power, right? That's what it's worth. You've gained 5 parts in 100 on it. Well, what's it worth in 2 years' time? Well, you have 2 years. After the first year, it's 1.05 times the amount of dollars. So you multiply by 1.5 again and get 1.5 squared. And that's how much it's worth. Third year, it's 1.05 to the third. And the T years from now, it's 1.05 to the Tth power. So interest works by multiplying 1.0 interest rate, right? Or 1 point interest rate to the Tth power into the future, okay? That's how interest works. And so, so discounting is patterned after this. So this is what I just said. If you have a percentage interest rate Z, and this many dollars is invested, in T years it's worth 1 plus Z over 100 to the Tth power. So that's what I just said. If Z is 5%, then it's 1 plus 5 over 100, or 1.05 to the Tth power. If the interest rate is negative 2%, which means you're losing money, then the money is worth 0.98 to the Tth power, which is 1 plus negative 2 over 100, all right? So that's the way interest works. And that's also the way zillions of other things work. It's the way exponential population growth works. It's the way in which the neutron density inside an atomic bomb work as it's exploding. And there are many, many things that have this kind of explosive exponential growth. It's the way in which radioactive material decays. It's got a negative interest rate and so on. It's a weird business in which change starts out looking slow and then gets explosively huge if it's growing. Seems to, from our perspective. And this is why the pandemic is so hard for people to get their heads around, because it grows exponentially when it's in boost phase. And people think all of a sudden it looks like it's just everywhere. And that's because it's been doubling. And all of a sudden, when it comes into your ken, it's like everywhere. Einstein famously said, here in town, it's amazing that exponential growth isn't illegal, all right? Because people can't understand it and it affects them so much. So the real interest rate, the growth rate of dollars, is actually built into the consumption values that we would have. So if we made a decision in 2019, I think, let's see. Oh yeah, good. If we made a decision in 2019, and then that was the consumption in 2020, and that's the consumption in 2021, the interest rate, the growth of the economy, the exponential growth rate of the economy is like built into that because it's dollars, all right? So think about growth in income, growth of the economy, and the interest rate as all being the same thing, even though in economics, they are very much not the same thing. For our purposes, they're just about the same thing. But it's also the case that in addition to money, people care differently about utility they're going to get in the future versus utility now. And the question is, how many cookies would I have to give you a month from now to make you take that offer over 10 cookies today? Now, maybe you don't want 10 cookies, but let's suppose you did want 10 cookies, all right? Or let's get something that you do want. And then you have to ask, well, if I'm going to get some today, what reward would make me put that off for a month? And would I need 11 cookies in a month, or 12 cookies in a month, or 13 cookies in a month, and so on? And that's called discounting. If you need more stuff in the future to compensate for something today, because you value the utility today more than today you value your future utility. That's the idea here, all right? So just like interest rates, economists assume that there is some quantity that discounts future utility inside your brain. Now, it turns out there really is something inside your brain that discounts future utility. And it's not just in your brain, but you can do experiments with animals, and it's inside animal brains too. And it's inside animal brains that have split off humans that go way back. Pigeons have the same discount rate that people who aren't trained in discounting have, and even the same functional form. And critically, it is not the functional form that economists use, all right? And that's actually interesting. So, but that's a separate story. So economists assume that there is some factor that discounts future utility, which is like a negative interest rate, all right? Just like a negative interest rate. And so there is some factor beta called the discount factor that's less than 1. And so the utility, say a year from now, is 0.95 times the utility this year if you got the same stuff. And the utility 2 years from now would be 0.95 times 0.95. And the utility t years from now would be 0.95 to the tth times the utility that you've got today to be equal to you in value. And the discount factor is approximately 1 minus d sub r, which is like the discount. It's called the discount rate. So if the discount rate is 2, it means that your utility, future utility, falls by 2% every year. And so that's 1 minus 2 parts in 100, or 0.98 in that case, all right? So the question is, how many cookies would I have to give you a month from now for you to choose that option over 1 cookie right now? And we've got some factor that is assumed to be operative that you can experiment with, and people do, in fact, downweight the future. but not in this way. But nonetheless, if they did do it in this way, this is what would happen. If the discount factor is 0.9, meaning there is a 10% down weighting of as each year passes, then 10 units of utility today, if you're going to get them now, are worth 10 units, 0.9 to the discount factor, 0.9 to the 0 times 10. But in 1 year, it's 0.9 to the first power times 10. And in 2 years, it's 0.9 to the second power times 10. And in 3 years, it's 0.9 to the third power times 10. And so the utility, 1 unit today is 10 units today would only be worth 9 units. If you got 10 units a year from now, it's only worth 9 units to you today. And if you're going to get 10 units 2 years from now, it's only worth 8.1 units to you today, right? You see how that's working? And it's kind of like interest, right? In that way, if you had a negative interest rate and you're going to go out and buy something with 10 bucks, right? That 10 bucks is not going to be worth the same amount 2 years from now. But this is not the same thing as that. You don't wait here. This is just internally how much next year is worth to you, all right? How much everybody's welfare, next year is worth to you. How much the sacred forest is worth to you next year and the year after that. There is a whole lot of abstract and extremely deep stuff that's embedded in this whole concept. And moreover, there's the assumption that the effects are multiplicative, discount factors to the teeth power. And so you don't, if it's worth half as much to you next year, it's going to be a quarter in 2 years and, an eighth in 3 years and so on. And so there's a lot here, but this is what's done. And so we can think about 2 radically different futures using this formalism, all right? Let's suppose in one, we place a tax on carbon emissions. Let's suppose the reconciliation bill comes through and we put an instant tax on carbon emissions. And so the economists model what that's going to do to the national wealth and somehow translates that into a consumption number that we're all happy with. And that's going to make 2021 consumption this green value here, and 2022 consumption this value, in 2023, so on. And if we say, well, how much are those future consumptions worth to us? Well, we'd say the 2021 consumption is just worth what it is, because this is 2021. But our 2022 consumption is going to be our discount factor to the first power times that utility. And in 2023, it's going to be the discount factor to the second power times that utility. And that discount factor, remember, is less than 1. So each of those years is getting less valuable. And moreover, it's not just consumption. There's this utility hanging out there. So it's the utility of that consumption that's really here. But this is what's done. And so we can figure out the net present utility value of all the future to us today. All right. And so this is what we're going to use to make the decision. And what we do is we compare that to an alternative future in which we don't mitigate climate change. And so it's oranger as a result. And we have consumptions there. They might start higher because we have more money to spend on social programs, for instance. But later on, they might really start to hurt because now everybody's dying from, wildfire and stuff. And so we've also got a utility series that comes from the consumption in the future plugged into the same utility function and discounted in the same way. And what people in government do is compare this to this. And the one they're supposed to choose is whichever one is bigger. How much happier are people, not just now, but all their future selves and all the future things they care about because of the decision, the green decision, say, versus the orange decision. And so the way that plays out in practice is we might have 2 different functions here. And these are functions that are hard to see on an arithmetic scale, in which the green one makes people much happier 200 years into the future. But if you look down here at the next 20 years, what you discover is that people are a little poorer down here than they are here because we've spent money mitigating climate change. Now, what we're going to find out later is that the technology has changed so much that that isn't true anymore, okay? We're actually not going to be poorer, all right? It's because the stuff we're replacing it with is cheaper. But if the reconciliation bill goes through the way it's supposed, well, the way it was, the way the current draft is in Congress, not the Manchin cinema pushback against it, then it may well cost us more now upfront. And that's because instead of doing something that would be cheaper for the government and perhaps cheaper for society, we're going to probably do something economically inefficient that fits underneath the rules of budget reconciliation, all right? And underneath the political realities of opposition to a carbon tax and so on. But nonetheless, this is the general idea. What we're typically doing in the environment is trading off costs up front for long-term benefit, particularly with something like climate change. That's been the historical pattern. And so how do they work? Well, let's suppose there are two discount rates. One is 5%, one is 10%. With the 5% discount rate, what you do is you add up utility this year, utility next year, utility next year, utility next year, you just add them all up, but multiplied by beta to some power. For a 5% discount rate, it's 0.95, 1 minus 5 over 100. So you're discounting at 5% per year. Next year's worth 95% of this year. 2 years from now, it's worth 0.95 squared and so on. So you add that up and you get these two numbers if you actually do the math. Green wins, 5% discount rate. But with a 10% discount rate, it's 27 versus 137, and orange wins. And that's because if future utility is discounted away quickly, decays away quickly, you care more about the upfront costs than you do about the more distant benefits. So arguments about what discount rate the federal government should have to use are the sort of stalking horse for real arguments about whether or not you want to do it and why, all right? And those arguments, if taken literally, should be all about the ethics of future generations versus today and all kinds of things, but they're really about something else. But nonetheless, this is what's done, all right? And so as we'll see in a minute, the discount rate that the government uses is something that is a political football, all right? And so what'll happen is the Trump administration increased the discount rate relative to the Obama administration, and Biden dropped it back down again, meaning it favors collective decisions and decisions that cost money up front but are supposed to save you money later. That's the idea. Okay. So in general, a low discount rate will favor action today to mitigate future nexus damages, whereas a high discount rate will put off mitigation in favor of actions that increase immediate utility. Now, to translate this into the actual rates that the government uses, believe it or not, this is actually done a lot of the time still this way. It's due to a guy from the 20s whose name was Ramsey, who was a real smart guy. You should read his original paper if you're a mathy person. It's actually an enjoyable read because the mathematical proofs in it have amazing subtlety, all right? They're really beautiful if you're into that kind of beauty. So anyway, but there are a couple of rules about economics models that I have. Economists always want a snappy mathematical formula. And that means that there's this ethic to get a snappy, simple result in a mathematically crisp form. And you're willing to chuck almost anything. This is overly disparaging probably, but maybe not. You're willing to chuck over all kinds of stuff overboard if it leads to that snappy answer. The ethics of the field point towards the elegant mathematical result. And in my view, this is well, and there's a real movement in economics away from this kind of work for that reason. And the second thing is that, at least subliminally, they want as many things as possible to look like compound interest, which is where they came from and what they understand and what their consultancy clients are interested in. And so Ramsey went to work on the formula for discounted utility using these two rules. I want a snappy formula. This is in the pre-computer age when there was no other choice. And also, I want things to look like compound interest. So this slide has a lot of stuff on it. And I'm going to read it through. If you don't understand it, just forgive me. I guess that's what I was going to ask for forgiveness. Sorry, rather than anything else. Okay, suppose that an action causes consumption in year t, C of t, to change by an amount delta t, which may be positive or negative. So this is like I take some action for climate change, and in the future, it brings me a benefit. That means I'm richer, so delta t is positive, okay? The present utility value of these future changes in consumption are by definition equal to the utility in my current year plus the change, because I've assumed I've just made this change, plus beta to the first power, discounted to the first power, like if beta is 0.98, that's 0.98 times it, right? 2% discount, times the utility in the second year's consumption plus the change, plus beta squared times the utility or the consumption augmented by the third year of change, and so on, okay? And then what I want to do is I want to subtract off the utilities discounted in the future and their sum without the change in future consumption, without the change, okay? You see that? And that's because I want to know, did the change give me a positive or a negative benefit? And how big was it? So I want to take the future utility with the change minus the future utility summed up, net present value of it without the change. And I want to ask, what's that thing? Is the change worth it? Am I happier today because of it? That's what you're really saying, including all of the things I care about the future. And this is, of course, gnarly, all right, because who knows what any of these things are? I mean, really, okay? All right, who knows what any of these things are? Let alone the fact that we have different values, and so your calculation is going to be different than mine. But nonetheless, there it is, all right? Now, if consumption were to somehow just grow like interest rates, if consumption just is growing like interest, and so we're only interested in economic growth, and G is the economic growth rate, like 2%, 1 plus 0.02, 2 over 100, the growth rate here, to the first power in 1 year and to the second power in 2 years, where G is the percentage interest rate over 100, and so on, then of course, that's what an economist wants. And so what Ramsey did was to figure out that if delta is small, it can derive a function, a thing, a quantity that's just like interest, that only discounts future consumption, and where we then don't have to worry about any of the rest of this stuff anymore, all right? That somehow magically takes care of it all right? So that's the idea. And so can we make this simple, at least for a small change? And what he discovered, what he showed, what he proved, was that for a small change, we could take the utility currently is equal to the change in consumption this year, plus some factor beta to the first power times the change in consumption next year, plus and so on, okay? And so this, I fixed that in some version of this, but it wasn't fixed. So let me fix it. Let me edit it right now. What this should be done, what should be done with this, oh no, I guess it's okay. There's just one, yeah, there's a, this plus and this parenthesis, and that plus should all be taken out. The plus parenthesis plus, that should just be this quantity times this one, okay? So somehow in the editing for this and transfer of a couple of different files that stayed in. So X out plus parenthesis plus, and then it's okay. And this should be times beta $ to the third power, this one right here, all right? So I will change that in the one that's online. I actually think that it has it correctly. There's no time to change it now. So this looks just like interest. It's the change in money times beta to the 0th power plus the change in money times beta to the 1st power plus the change in money times beta to the 2nd power plus the change in money times beta to the 3rd power. And that gives me net present value of all my future happiness somehow magically. Now, how can, yeah, go ahead. This should be delta 2021 plus beta to the 1st power times delta 2022 plus beta to the 2nd power times delta 2023 and so on. Yeah, so if we just got rid of this plus sign, it is also, no, we're still missing a parenthesis. Okay. Yeah, we have to get rid of that plus and that parenthesis. Have to cross those out to make that right. So we have utility is approximately equal to the change in consumption this year plus this beta $ thing times 2022's times the change in consumption in 2022 plus beta $ to the 2nd power times the change in consumption 2023 plus ... Okay, we're all years. That's what it should look like. All right, sorry about that. And this beta is just a discount factor, so it's 1 minus a discount rate. And the discount rate, so if beta is 0.98, I care about utility next year at 10% or at 2% less than I do this year, so it's 0.98. 1 minus D $, that would be 2 over 100. Ramsey's formula is that this number, which when plugged into here determines this number, which when plugged into here determines future utility, is equal to this thing. And all of the ethics, all of the concern about the poor, all the balancing of current and future generations, everything is bundled into this, the DR $, the discount rate, about how we discount the future. And that somehow magically translates consumption into present happiness if we sum up all those future years. All right? If this sounds arcane and weird, it's because it is. Now, this is the important thing. What are these terms? So the discount rate, it's like, well, what do we, if the discount rate is 0.02, it means it's a 2% discounting of future utility. And that turns out to be equal to this discount rate, which is just the discount rate that I talked about before, your pure time in your head discount rate. How many cookies? It's the how many cookies problem. All right, how many cookies do you want today? How much do you value personal consumption? Times the economic growth rate of the economy, times CIA, which is not Central Intelligence Agency, it is the coefficient of inequality aversion. And it measures how curvy the utility function is. Remember, the curvier it is, the more you want to give equally. And it's because giving to a poor person increases the utility more than giving to a rich person. So the claim is that this discount rate, which you can use just to discount future dollars that are the consequence of some policy, somehow balances both your internal regard for today versus the future and your internal decision about how much you want to be egalitarian and redistributive, and economic growth concerns. They're all in there in like this snappy formula, okay? And so the big studies that are out there that come to different conclusions about how much climate mitigation we should do are actually using this formula and assuming different values for the different terms and coming up with a big discount of the future or a small discount of the future, which determines the outcome about whether or not you want to mitigate climate now or later, right? That's the thing. So, so there it is, all right? And so you can see why I'm giving you some way to choose around this, all right? Okay, but the important thing is, if you want to do one thing, kind of memorize this, that you're discounting the future. It's 1 minus the discount rate raised to a power times future consumption. And this thing, this discount rate here is the sum of the pure time discount rate, economic growth rate, and this curviness measure. Okay, this leads to what I call dueling liberal values, and we're almost done here, all right? If you want the discount rate to be small, remember, if the discount rate is small, then you care a lot about future harms because you haven't lost your interest. Your interest in the future hasn't decayed away, right? Still stays high. Then if I want this to be small, if I'm going to get, if I'm working backwards to a discount rate I want to get something passed that is climate mitigation, say, and I want this to be small, then I want this number to be small. And this will promote action to mitigate climate change. But I also want this product to be small. And that means that I want the curviness of the utility function to be small, which means that I actually want to push my utility function into the domain where it becomes more linear and I don't care about poor people anymore. All right? And so this thing actually leads to tension within liberal and conservative communities for that case, all right? For that reason. There are a couple of famous things that dominated the 2010s. And there were two competing economists who came up with very different carbon prices that would be optimal to maximize utility using this formula, all right? One was Bill Nordhaus at Yale, who won the Nobel Prize for all of this. And the other one was a guy named Nick Stern, who's in the UK, who's been made like the head of everything. And he's now Sir Nicholas Stern in the UK, okay? So they both were heaped with laurels for this brilliant insights. Now, Stern assumed a discount rate of 0.001. He says people care about the future. Only 1 part in 1,000 goes away for next year and the year, you know, like that. Nordhaus assumed it was 15%, not a tenth of a, I'm sorry, 1.5%, not a tenth of a percent, fully 15 times bigger. Stern assumed the economic growth rate was 0.013, Nordhaus 0.015. Those are in the right direction, but those are constrained by data, so you can't really fiddle there, okay? And finally, Stern assumed the coefficient of inequality aversion was this smaller number 1, whereas Nordhaus assumed it was almost twice as large, okay? So Nordhaus actually really cares about the poor here, and Stern doesn't care about it at all here, but Stern says, oh yeah, the poor really care about the future, and Nordhaus says they don't, okay? And as a result, they came up with these discount rates that are very different, 1.4% versus 4%, and that translates into an optimal CO2 price of $70 versus 20. $70 gets the energy transition done, $20 doesn't, full stop, okay? And so it was argued about. And so this discount rate is the primary determinant historically of the price on carbon that is optimal. We're just about done. Obama assumed the price on carbon was $50. He had a relatively small discount rate that underpinned it. Trump lowered that to between $1 and $7 because of uncertainty about the discount rate. The National Academy of Sciences looked at this using a range of methods that don't include this anymore and conclude that it's between 56 and 171, but you can see how discount rate dependent that is. 3% gives you 56, 2% gives you 171. Biden, right now, they're trying to decide what it's going to be set at. And so this stuff is hotly debated, but it's, in my view, a stalking horse for other arguments that are really being had. Thanks for bearing with me. I promise I won't do this again. Okay. All right. So